the invitation. So I'll talk about polar codes, but rather than the details of the code construction, I'll mainly discuss the math results that are underneath the construction of these codes, which are very recent. If you were at the seminar at Princeton a couple of weeks ago or 10 days ago, I may not advise you to stay. There's significant overlap. So yeah, so the codes are based on the result of polarization. This is, I will explain this name in a bit, and today I will present the result over GF2 to the M. Then I hope I'll cover more than I did in Princeton about Z and R. Okay, so that's the plan. So I'll tell you what's those polarization results. Okay, so start with n random variable, which are IID, Bernoulli P. And build the vector x, which is the column vector with those n random variable. Now, all the theory of polar code is around this matrix here, which is a 1, 1, 0, 1 matrix, to which you take many tensor product. Okay, so say n is the power of 2. All right, so this is an n by n matrix, and you apply, you transform x with this matrix to obtain the new vector y. All right. So why is this transform interesting? So let's look at what happens to the entropy of this vector. So entropy, the entropy is the Shannon entropy in this talk. So entropy of a distribution P or mu is the sum over all the x in the support of mu of mu x log 1 over mu x. Let's take log base 2 for now. So that the entropy of a binary random variable is between 0 and 1. It's 0 if it's deterministic, it's a delta, and it's 1 if it's uniform. So now the entropy of x, of the random vector x, because the components are IID, is just n times the entropy in one of these components, which is governed by this parameter, n times the entropy of the Bernoulli P random variable. And the entropy of y, well, it's not the sum of the entropy of each component in y, because there's dependency. That's the goal. You are creating dependencies in that vector y, but it's always true that this is the sum between of the ith component given that you have the past. It's just factorizing the distribution in this way here. Okay, so now what's interesting about this vector y as opposed to x is that here the randomness is uniformly spread out in each component, while here, and this is the polarization phenomena, for most I this tends to 0 or 1. So formally this is the result. So it's due to Arikan, this version. This result came out around 07, 08. This one was published in, I think, 08 or even 09, perhaps. And it says the following, that for any epsilon that you pick, if you look at all these components, all from 1 to n, such that, so this means the components up to I minus 1 are moderate. They are between epsilon and 1 minus epsilon. If you look at this set, its cardinality is ON, little o of n. So there's a vanishing fraction which is not in the extreme of 0 and 1. So that's where the name comes from, polarization. It takes the randomness and brings it to the extremes. Okay, so the second thing you can say is that this still works if you take epsilon that scales like 2 minus n to the beta, where beta has to be less than half. Okay. So roughly 2 minus square root of n. So it's pretty fast. You can take epsilon that goes exponentially in the square root of n, and this still holds. You still polarize the components. All right.
Which set goes to 0 to
Yeah, so that's one of the questions. So first thing to observe is that which one goes to 0, 1 is only depending on p, right? So for a given dimension and for a given p, you can compute these values is the chart of who goes to 0 and 1. This is not realization dependent. It doesn't depend on the values of these xi's. So this is computed once for all. Now the question is, the mathematical structure is not well understood. That's one of the main open, I think, problem on this topic. But we have efficient algorithm to compute these for a given n and for a given p, linear time. Although I'll comment a bit more about that. Let me just say why how it applies to some application of this phenomena. So the first corollary is like if you define the deterministic components to be these components for which the conditional entropy is less than delta, less than epsilon. These are the components that are very low entropy for some epsilon. Okay. And if you try to guess, yes?
That's shorthand for condition of y1 up to y.
Yeah, this is up to y minus 1, yeah. So if you define that set, and if now you try to guess y, the entire vector y from observing that set. Sorry, from observing any but these components, the complement of that set, and try to guess the entire y. So basically, you're trying to guess the component that are in this set D. And if you do the estimate that minimizes the probability of error, which is the maximum likelihood estimate, so for you observe a realization of this, you find the maximum likelihood value for that, okay? And then there's a probability of error in doing that, and you average that over all possible realization. This will be less than n times epsilon because of the fact that each component in here has to be less than epsilon. And since epsilon can be exponentially small, this can be also exponentially small for beta less than half. So this says that you can see how this can be used for compression. If you have this long string, which is ID Bernoulli P, then what you do is you transform the string with this map Gn, and then you disregard all these components here that are very deterministic for your threshold parameter that tells you that's going to govern your error probability. You don't take those. You only store those ones that are actually that are not deterministic. Those ones, and these ones you can recover. That's one thing. Okay, you can recover them very reliably.
Yeah, but not so. I mean, maximum likelihood may not be efficient.
Yeah. So that's the first thing. If you want to compute that, maximum likelihood, it's what this is of the order n components. So if you have to maximize this, it's 2 to the n exponential search. But because of the structure of this matrix, which is heavily structured, this will be only n log n. That's why these codes are interesting. So, because when you compute this marginal, you will break it down into a divide and conquer type of algorithm. So the decoding will be only n log n. The encoding is clearly n log n. It's a matrix that is applied recursively. It's n log n. Decoding is also n log n.
Isn't there n epsilon bits required to describe everything?
Isn't there what, sorry?
So like the entropy of y over d is like n times epsilon.
Yeah.
Bits. So shouldn't your probability of error be?
Well, why is that bits?
Because the entropy was epsilon for each component.
Yeah. So this is a bound on the probability of error. It's not a measure of information. There's no bits.
Yeah, the way you wrote it, it's not clear that it's a probability of error.
Oh, I see.
Yeah.
Well, if epsilon is small,
No,
so it's a union bound, and each so basically here is what is behind that. If you try to estimate a random variable x from observing a random variable y, then the probability that you make an error in estimating x from y is less than the entropy of x given y, where this is defined by being for a given realization, for a given little y, this is 1 minus the max of this distribution. This is the probability of error because you declare the max. So you maximize you maximize over all little x p of c that x is equal to x, given that y is equal to y. This is your maximum likelihood estimate. 1 minus this is your probability that you make an error.
I think the only unclear thing is that PE, this notation you have, is PE is the probability of error.
I
it's
see.
not the probability.
Okay,
So
okay,
it's like
sorry.
PR.
Yeah, so maybe I should say that this is the error. So, okay, the other observation is if you look at questions.
Does this which variables are tends to 0, which one tends to 1 depends on how you enumerate on y1 to yn?
Yeah. So here we are going top to down. If you take a random permutation, if you start with y7 and then y2 given y7, this may not happen. We know two orders where this happens. There's top to down and there's a bit reversal. So if you enumerate your components, let's say we are going from 0 up to n minus 1. This is all 0 string, this is all 1 string. You can go top to down, or you can go in the order of bit reversal. So if you reverse those and you go along that order, you still have the polarization pattern. This is because this matrix Gn is invariant under a bit reversal permutation.
Yes, but it's somehow the coordinates are dependent on the binary. It's binary element. It's not really dependent on its integer. Right?
Yeah, it's binary. Yeah, it's binary. We'll see the integer at the end if we get there. What happens there? It's a bit more complicated here. So the other corollary is that okay, if you take now the random components, so these are defined for an epsilon, such that the entropy of the ith component given all the past is this time more than 1 minus epsilon. So these are the high entropy ones. Then if the difference in those two is actually the vanishing fraction. So the figure looks a bit like that. If you plot, here I'm going to plot the component I, let's say from 1 to some power of 2. And if you plot here the conditional entropy of yi given yi minus 1, this looks a bit roughly like that. You have many components which are equal to 1 at the beginning. The first component must be going to 1. It's the XOR of many Bernoulli p bits. And then, so you have a few, this is the vanishing fraction. There's some waterfall. And you have a concentration of values close to 0 or 1. And if you zoom in into the pattern of who's 1, for example, here, it looks fractal-like. So you have patterns that you find in the same types of pattern that you find in different locations, and same here. So this is what we don't understand. What's the mathematical structure of these components? And this is the little o of n fraction. So now what I'm defining here is I'm looking at, this was the deterministic components, and now this is a random components, very close to 1. And if you look at y on these components, so this means the random vector y restricted to the component indexed by r. This is IID, this is uniform, epsilon, and uniform. So again, this is like 2 minus square root of n uniform. And uniform.
That's L1 distance.
L1.
Uniform
Yeah,
distribution.
you have it for entropy, and this implies by Pin's curve for L1.
And what fraction goes to 1 and what goes to 0?
Very good. So you can tell directly because of this balance equation that we have, right? N times h of p has to be equal to the sum of the entropy of yi given yi minus 1. So how many? These are 0 or 1. The number of 1 is n times h of p. So basically, both these sets, if you look at both the counity of R and also the county of D, so R and H of P. And same for D. Sorry, same for D complement. So in both cases, you obtain, in the compression, you obtain a way to compress at the optimal rate, which is Shannon entropy. This is how many bits you need to store is that many. So the rate is entropy, which you know you cannot beat by Shannon theorem, so it's tight. And in the extractor sense, of course, you obtain more than the mean entropy, but this is because it's an extremely simple type of source, very structured, highly Bernoulli P. However, again, if this extractor has the property of being invertible, from that source you can extract the pure bits. Now, if you want to get back to the original source, you can do this efficiently in n log n. So let me not stress extractors too much here. I'll talk a bit more about in the next. I want to prove now this result. If there are questions.
When you start with a larger than like a 2x2 matrix, do the patterns become any simpler for which bits polarize and which don't?
So if you start with 2x2 for G?
Yeah.
So if you start with 2x2, you mean you only have two random variables?
No. So instead of this, 1, 1, 0, 1.
Yeah.
You can also do the same process with like an,
arbitrary A, B, C, D. That's what you're saying?
Or K by, can't you do it with a K by K?
Yeah, you can do. Can do K by K.
Yeah.
Your number of symbols is K.
Yep.
Yeah, you can do K by K. You can actually K by K give you more reach, so you can boost that exponent from square root of n to exactly n by taking K by K. I can tell you more about that. At the end, it's still a negative result because to boost the exponent from n to the 0.5 to I think n to the 0.51. You need to, the first time this happens is with dimension 16 by 16, which means that the block length now, the dimension goes with like power of 16, which makes this absolutely not usable. However, so there's I recently worked on that here where you try to, where you play with these values and you don't work on GF2 but GFQ. There you can actually boost the exponent much more significantly by choosing this over GFQ carefully. And there's quite a bit of combinatorics behind that, but.
So you still don't know like codes which polar coding schemes which have constant distance, right? That would get you all the way up to.
You mean to get to the
constant worst case distance?
Yeah. So that's one of the issues. Yeah. So that's why you're stuck at square root of n. But it depends. Yeah. So it's still very good in terms of decay square root of n. Like application-wise, it's actually very nice. It's not really there that the issue is. So maybe I tell you, so the pros and cons. The good thing about the very strong property of this code is the following, is that the complexity for both encoding and decoding is n log n. And indeed, it's a constant. So the constant is 2 in that setting. And it does not blow up. So basically, if now you try to approach your entropy of compression rates, and say you are epsilon away of this, most of the existing scheme, many of them, when epsilon gets close to 0, the complexity in some way blows up. Here, this is 2 once for all. There's no increase, except a caveat, which I'm going to mention in a second. But the other good thing is that this is a completely deterministic construction once you have found those components. If you compare this to state-of-the-art like LDPC codes, so first of all, it's you need to draw at random the graph, but it's still turbo code LDPC is still conjectured, even in that basic setting that they achieve entropy of P with the BP decoding. With maximum likelihood decoding, we know they work all the way down here, but this is complex. If you want to do belief propagation, which is efficient, linear time, then it's still not known whether they achieve HFP. Still research on that today. The expander codes of Sipser and Spielmann have been proved after they proposed them. When they proposed them, they could not show that they were getting HFP. But later on, it's been proved that they get HFP, except that the scaling, it's linear complexity, but the scaling of the complexity with this gap is exponential.
Of what? Of the decoding algorithm?
Yeah. And of course, you need to find an expander. You need to construct. You need to draw the probabilistic method to construct the code.
It's not the same purpose in the LDPC and other. There are codes that are trying to encode the input, not to compress it. So
Yeah, it actually is.
So how do you view the polar
Yeah.
codes as
Yeah, good. Yes, true. I skipped that. I skipped that part, and I think it's usually skipped. But there is a way to understand coding on the BSC with this setting that I'm describing here. which is not often presented, but it's the following. Imagine that this is your code word X. This is your noise. These are vectors of size n. This is your noise, which is IID Bernoulli P. Okay, so this has nothing to do with what I was doing before. Okay? This is U, and this is the output. Input and output.
So you apply
Apply GN to that. It's linear map, so it applies to both. So what you are doing here is you are taking your noise vector is what I'm working with here, and you're trying to clear the noise in some components. You free it up, and some others become completely noisy. So what you do then on the components which have no noise, then you transmit information bits. On the very noisy one, you freeze the bit to be 0, so you're going to read the noise. So that's like syndrome decoding. So this is indeed mapped directly. It's exactly like a communication over the BSC problem. If you can extract those entropy bits with a linear map, then you have directly a BSC code. Yes?
So you said the complexity doesn't blow up when epsilon goes to 0, but doesn't n need to grow in order to have epsilon drive to 0?
Oh, so there's two things. Either you fix an epsilon, and then you let n grow, but this is dependent. And then there was the question of how fast can epsilon be made with respect to n, and this was exponential in the square root of n. But now you pick an epsilon that you want to work with, 10 minus 5. Then when n tends to infinity, eventually you will be there. You see the difference is that it could have been that the complexity also scales up with epsilon, which is not the case here. Now, if you want to go below the epsilon, everybody needs to let n tend to infinity. I mean, this has to happen for large enough n. However, the complexity does not get hurt by how close you want to be. Yes?
So you said LDBC codes with delay propagation are linear time encoding?
Yeah.
So if someone tomorrow showed that they do achieve
Yes.
Shannon capacity, then would there still be would there still be situations where people would want to use polar codes?
Yeah. So there's two different regimes. LDBC are defeating polar codes for short block lengths. For short block lengths, for n small, for n of like 1,000 or below, then LDBC I think are performing better.
Okay.
Although LDBC are now 60 years, maybe 50 years old. Polar codes are like a couple of years old. So this is like the brute version of polar codes. People are working on improvements. So, but yes, LDBC at short block lengths are better. So besides this mathematical property, which matters apparently in some application like storage and things like that, where people want to have guarantees for the probability of error. But besides that, LDBC are better for short block lengths. For large block lengths, and this is data storage typically, where block lengths can be 10 to the 10 or really, really huge, then polar codes perform better. So it depends. Now the questions become a bit trickier in terms of applications, but there are different regimes where these two.
When you say perform better, you mean like empirically, or you mean like the theorems are better for polar?
No, theorems would be the same. Assuming LDBC gets us there, theorems will be the two same. Now it's all empirical. It's no longer about the theorems, about how they perform. Yes?
I might have asked this last time, but if you consider, suppose that you don't know what P is going to be, but you just have like an upper bound of what P is going to be in your application.
Uh-huh.
Does the set of coordinates with reasonable entropy, does that behave monotonically?
Yes, it does. So basically, if you look at those points for a fixed n, and this is for a value of p, if now you increase p, this is let's say p is less than half, and you increase p closer to half, then all these points they raise up all monotonically. So there's no. That's a nice property. So
That seems non-trivial to show. I mean, why is that true?
it's not that hard. I can show it to you.
Okay, yeah,
maybe at the end of the talk, I can show you the proof of that. It's not very hard. It's true that it's surprising that it's kind of a good luck that we have that property, but the proof at the end is not very hard. So I just want to prove you the result and then say some of these other results. So the proof works as follows. So you start with
Sorry, what are you proving now?
sorry, I'm proving the first part here, the theorem, that you must go to 0, 1. So you start with let's say, you pick a P and pick an entropy. So this is your parameters. If you try with only that means we are considering entropy of x1, x2 is the same as the entropy of y1 plus entropy of y2 given y1. This is twice the entropy of P. So y1, what is y1, y2 is you take x1, x2 and you apply it to this matrix. Okay, the XOR of x1, x2, and just you leave x2 untouched. So now the entropy of y1 is exactly the entropy of x1 plus x2. This must increase compared to where you were. So that means that this is entropy of y1 somewhere closer to 1. And now because of this balance equation, this must be the y2 given y1. This one here must be exactly at the symmetric part here, right? Because these two numbers must average to where you were at the beginning. Now if you go to dimension 4, so let's maybe just do the first one. This is your matrix G4, which you apply to x1, x2, x3, x4. So this becomes, the first component is the XOR of all of them. The second is x2 plus x4. So this is y1 and this is y2. Okay. So the entropy of y1 is going to be the XOR of these two. Sorry, I want to take these two random variables. You can look at this as being the XOR of x1, x3. This is your new x tilde. And you XOR it with the sum of two previous bits. And here is one of them. So this looks again like basically you are splitting this again into two components. This will be entropy of y1. So here normally I should put a time 1, this is a time 2, okay, but let me use the same notation, y2 given y1. And this one we split into two other components, and all of these you can check has to be always splitting equally distantly. Okay. So
Wait, are they the two different triangles have the same distance?
yeah, so you always have the same distance here, like here, but this distance might be not the same. So for a given p, this is computed once for all. You can compute for a given n and a given p, you can compute these values here. And you have the property that these two will always average the previous one. So you have this recursive structure. Now put a random process that travels in that tree with probably half to the right and half to the left. And let's call eta k this random process, where k is log, so k is log to n. So this is k is equal to 1, 2, 3. Now eta k is a martingale because its expectation with respect to that left-right filtration is exactly where you were before, because you go half to the left and right. And it's bounded. It must live between 0 and 1, so it must converge. And if it converges, it means that if you look at the gap where you are next compared to where you are next and where you were before, this goes to 0 almost surely when k tends to infinity. So now these two expression is the process where you k plus 1 is where you are next compared to where you are before. Okay, this is this gap where you are next compared to where you were before. So for example, at the step 1, and since this is the same as this, you can also, this is where you are next, where you are before here, and these are the same lengths. So at step 1, this would be exactly, for example, something like this. Entropy of x plus a copy of x minus entropy of x. This will be what it looks for k is equal to 1. For k which is not 1, you just insert some conditioning in here, but it always looks like that. So there are, this is the appropriate path, depends on k, and this is always going to be the XOR of 2 and one of them single here. So now since this goes to 0, it means that for any epsilon you pick, eventually this must be below that epsilon. So what does it mean? Let's ignore this path for now. What does it mean that you have two random variables which are IID copies, binary, and such that this must be arbitrarily small? But this is easily to check because, again, it's XOR, so there's no degree of freedom that blow up. There's two cases. Either x is deterministic, in which you get 0 minus 0, it's small, or x is uniform, and then the XOR is still uniform, so it's 1 minus 1, which is small. And you can plot that curve for arbitrary p. It's like that. The only way you get close to 0, 1 is at this extreme. The only way you get close to 0. Now, with the path, turns out that it's even in your favor. This is still true. There's a small convexity argument that I'm skipping here. But this is kind of the case to check. And then you can show that this also implies that this must be true if you have some condition, some variables in the conditioning. So that means that random process.
But in this conditioning, x depends only on yk, and x
Yes.
prime depends only on yk.
Yeah, that's very important, indeed. These two are IID. Sorry, that's very important. Thanks. So nk goes to sorry, yeah, let me just finish and then I take the question. So the nk goes to, this implies that nk goes to 0, 1 almost surely. And then you are done, because the probability that if you, that random process has a uniform distribution on the leaves, because it goes left and right with probability half. So what we had to compute, which I just erased, the number of components for which this is moderate, this number divided by n is exactly the probability that this process nk, where k is log n, ends up in epsilon 1 minus epsilon. So this goes to 0. So this goes to 0. That's the trick. Yes?
So you told that here is all really with history. So does it true that without history it tends to 1 and to 0, or it seems that it's not true?
No, the two extremes to 0 and 1. The very first term and the very last term given the past always go respectively to 1 and 0. But if now you ask me for dimension 2024, where does the 372 component given the past go, I can't tell, because this random works.
No, but my question is, so here your argument will work without remembering history.
So without removing the history?
So
Oh, I see. That is the history, right?
Yes.
Yeah.
So you told that without history you still goes to converge.
Yeah, no, you can't talk about without the history. This process must be with history. All I was saying here is that I'm claiming that if this is small, then this must be close to 0, 1. And I'm only arguing this in the case where you didn't have history. So the proof is incomplete, and you just have to trust that this behaves in the same way that if this is small, then this also must be close to 0, 1. But it's clear when you don't have conditioning, and small computations imply it with the conditioning. So yeah, so the proof is basically this argument. Now I'll tell you about the GF2 to the n.
How do you get the square root n?
Yeah, the square root n is basically you show that process that I'm defining here behave roughly like it's either going to be squaring the previous process, or you can find a new process that behaves like that as an upper bound, or you double it. So if you have a process that, let's say you don't have the 2, if the process either squares with probability half or stay where you are, this would be exactly square root of n in the decay, because you square but only half the time. And because of the 2, you have that little beta here. So roughly it goes like that.
So it's explicit analysis on the increment, or on the
Yeah, you have to analyze the current. So for GF2 to the m, here is the setting. It's exactly like before. Define x1, xn to be IID random variables, but now they are IID over from a distribution mu, which is on GF2 to the m. So you fix m. This is fixed, doesn't grow. And so basically, this is not a random vector, but it's a random matrix. So each of these are m bits. Each of these n random variables are m bits. And there's an arbitrary dependency structure on these m bits. So define, like before, y1 up to yn to be the matrix gn times this. So I'm applying gn to the left. So it's like, yeah, I'm applying this to the first component of any second component, etc. of these bits. you still have the same chain rule property, meaning the entropy of this n sequence this is always the same as that. This is an invertible map. This is still n times the entropy of the distribution you have mu now. It's not Bernoulli P, but it's this arbitrary mu. And this is the same as the entropy of the ith row, given that you have observed the previous row. So now, these values are in general between 0 and m, because my entropy is log base 2. So it's 0 if this m bit vector is deterministic, and it's m if it's uniform. If this were to be just behaving like polar codes, one would perhaps guess that this goes to the extreme, either deterministic or purely uniform.
But it probably depends on the distribution.
Yeah. And
for example, if they're always 0 in the first coordinate.
Yes. So indeed, this cannot happen because of what you said. But what you can show is that this must go to a quantized value. It must go to an integer between 0 and m. That's sort of what the polarization brings in that setting. So then it
Can you infer it just by acting on one bit at a time, one column at a time?
You can do this if these were independent, for example. Yes. If this is a product measure, then this is just exactly applying previous result to each column.
Even if you condition,
Otherwise, you have to do conditionally, yes. But if you do, that means you have to do this column, and then given that column, you have to do the next one, and etc. But what if you want to do this jointly? You want to look at the ith row given the past, not in that order, but really in that order, like before. So then you obtain that, and then it raises the question of what does it mean to have a random vector of dimension m, whose entropy is quantized. Indeed, you can show that the entropy of yi on any subset of the m variable, given the past, has to be quantized.
What's the notation? Yi?
So this means the ith row restricted only to the component the component indexed by the set S. So S is a subset of M. You only look at these components here.
And sorry, you mean in 0, 1 to the size of S?
Thank you.
Above?
Yes. Thank you. Yeah.
Okay.
It cannot
I mean,
exceed
it's
S.
the same conditioning argument here, but
Yeah,
now
exactly.
it's marginalized over
Yeah.
the missing coordinates.
Yes,
right?
exactly. Yeah. So then I just want to make a side comment here about this problem, because I think it actually connects to some interesting combinatorial expressions. So side comment, you have mu, which is a distribution on not gf2 to the m, but a finite set to the power m. So x is just a finite set. Mu is on m bits on these finite sets. Now define this map, which is h of mu, which takes all subset of m. Yeah, because it will be an entropy, but yeah, it's not ideal. It's not ideal. But it's not too far from what it is. So it takes a subset and maps it to the entropy of mu restricted on the components indexed by S. So this means that if x1 up to xm is your m bits distributed according to m, this is just the entropy of the xi's, where I is in the set S. See, now, assume that this map. So the question is, we want to characterize when is this map integral? For what type of distribution mu is this integral?
It must be just supported on a subset.
Yes, but can we say more than that? That's what I want to characterize.
If it's concentrated on the subset of coordinates, and it's uniform on that subset. Right?
Yes, it's uniform that subset.
No, but what about
But
the,
what about-
the converse, right?
Okay, so
Yes, I don't. I mean, it seems like one possible character. There's nothing else.
Ah, yeah. Well, I mean,
no, but you also have to take into account the fact that any subset is integer.
so there's.
So
this
there's-
result,
I want-
So if you are uniform, if you pick just one
Yeah.
subset of coordinates, you are uniform there.
The rest is fully dependent.
Fully dependent.
Yeah.
That's only one case. Where
Yes,
So
that's
there's
one
also
case.
this thing
Yeah.
called, like,
it should be
Di-Finetti's
the only
theorem.
one.
Yeah, you want to show that it can only happen that way.
I mean, there's this thing called like Di-Finetti's theorem, right, where you have exchangeability that
Oh, I see. I don't know.
I mean, it seems like when you have integral entropies, you have some exchangeability properties, right?
Yes.
It doesn't matter which order.
Oh, so
So then, like, these Di-Finetti things tell you that there's some, variable you can marginalize over that, condition on that variable, you have to be.
yeah, so we will need to use such properties of the entropy to characterize what this exactly means. But basically, so the conditions we know about this map H of mu is that it's monotone. If you take a bigger set, the entropy can only increase. It's submodular. It's submodular, and okay, I'm not defining here. So this is exactly defining a polymetroid.
And it's integral.
It's now, if it's integral, it's exactly a metroid. So the question we are asking here is, given a metroid, because it satisfies this, when is a metroid representable with a distribution function? That's the question I want to answer. You can ask, when is a metroid representable with a graph or with a linear matrix, with a matrix? Here is, when can you represent a metroid with a distribution?
So do you have any example when it's not just
Yeah.
uniform and a subset?
So let's just see an example. So imagine that you just have m is equal to 2. Then the only case, okay, you can have everything is deterministic. You can have deterministic, and so this is entropy of x1 here, entropy of x2, and entropy of x1 comma x2. This is all the possible subsets. So this means deterministic, random, and random for x1, x2. Then you can have this case, which is they're both fully random, the bits, and they're independent. And then you have this case, which is interesting, which is that they're both fully random, but they're fully dependent. Okay, so.
Oh, so just, I see. So linear subspace is, yeah, sorry.
Right,
So
so
when
this-
we looked at just uniform on a subset of coordinates is a special case
Yeah.
of being uniform on a linear subspace.
Yes.
That would give
Yes.
some integral. So
Yes, I think this is, yeah.
Yeah, maybe that's a better conjecture.
But this is like what Horizon is Di-Finetti. I mean, this is like conditioning on what, you have a hidden variable which conditions on the parity or doesn't, and then you have.
Yeah, so the party, I'm not sure I understand definitely, but what is clear here is that in such a situation, what you know is XOR. So although there's no algebraic structure on that, this is just a finite set. The entropy doesn't care what the support is. It's just two. Here is x, in that example, x is, let's say, is 2. But what this means is that what you're basically saying, it's as if you know the XOR of these 2 bits. So the theorem that you can show is the following. So define an entropic to be a metroid to be entropic if there exists a distribution, and let's say it's 2 entropic if there exists a distribution on a support of size 2, such that it realizes your metroid. So it's not hard to show. This is done in 12. That this is exactly the set of GF2 representable metroid. So it's 1-to-1. Yeah, just subspaces. So to answer your question is so U24, which is the 4-point line. So this is a metroid of ground set 4. Any 2 points has a line that go through it. So the rank of any subset of 2 or more points is 2. This cannot be entropic, for example. So this cannot be linear, of course, because if it has to be linear, since it has rank, so there's four elements. If it were to be linear of rank 2, you can never represent this with 4 binary random vectors, because this has to be rank 2, this also, and this also. But then you're only left with one choice, which is a 0, 0 vector, which has rank 0.
What are the values in this matrix?
So if this was so this is the metroid with any elements of rank of size 2 or more as rank 2, and any element of single size as rank 1. So any elements are active.
That's a representation for the U24.
This is U24. So now it's clearly not representable over GF2. It's representable over GF3 because this matrix over GF3, any 2 columns has rank 2, any 3, and any 4. But now, why is this metroid not entropic? You can see it like that. So that it's not entropic, it means that there's no way to find a mu such that the entropy of x1 and x2 or xi and xj has to be 2 for any I and j. And also the entropy of the 4 random variable has to be 2. And also the 3, but just look at these two. This means, let's use here 1 and 2. This means that if you take the distribution mu, and if you marginalize it over x1, x2, this has to be a quarter, because the fact that this is 2 means that these two are ID Bernoulli halves. And this you can write like that. You can say that x1, x2 given x3, x4 has to be 0. Because you can, this is like the properties of, these properties of entropy that matters here. This means that if you give me any 2 realization, I can guess the 2 others. Because that 0 entropy means this is a delta. I mean, so if you give me, for example, if you're given x3, x4, mu of x1, x2 given x3, x4 has to be, this means has to be a delta. There's only one point here which cannot be 0. Or equivalently, if you don't put the conditioning but use that, this has to be a delta times 1/4. So now I want to argue that you can never have a distribution that satisfies this property. So you can put all the sequences of size 4. So this is all the x1, x2, x3, x4. There's the all 0 sequence. Then there are all the sequence with there are sequences with 2, 0. And then there's the sequences that have only 1, 0. And then there's all one sequence. Mu has to be positive somewhere because it's not, it has some entropy. So let's say that mu is a quarter here, and it has to be quarter. Because of this rule here, it means that if you freeze any 2 component here and you let these 2 vary, this must be 0 probability because you must be able to guess 2 of them. So freezing these 2 means that since you can freeze any 2 you want here, any sequence that has 2, 0 must have 0 probability here. Now, the second condition here tells you that if you freeze 2 components and you average out the other ones, it must be a quarter. So again, if I take those 2 which I freeze and I average out over all these possible values, you must hit only that part of the sequence because there's no 0, 1 is only appearing here or in that block here. So all these must be a quarter, which is not possible because this is like more than 1. So it cannot be a probability distribution. So this is a metroid. The U24 is not entropic. And then you can show actually that you can use the theorem of Tooth. That says that a metroid is representable over GF2 if and only if U24 is not a minor of it. So what we have proved here is not a minor, it's not a restriction, and you have to prove it's not a contraction, which is a minor in the dual. And because of this property of entropy with the same type of argument, this also works. So what this means in terms of the polar code is that now if you look at your ith row, I think you always have a size of maximal. This is more than what we need, but actually this is necessary to prove the exponential rate. But what this means in terms of the compression is that if you have this source and you do your polarization, then it won't look, it's not like each row of y is completely random. Not each row is completely random or completely deterministic, but there's always a pattern which is not the same, but there's a pattern of random components. And that pattern is what you need to store for compression. And this is also an extractor. So these bits are Bernoulli half, uniform, with, again, the same 2 minus square root of n.
The elements of the subspace you are generating.
Yeah.
So you have a linear subspace.
Yes.
And that's the non-constant rows will be elements from your linear subspace.
Yeah, so basically, one way to write this is like that. It's just that, so for any I, for any epsilon, if you look, you can look at the entropy of the ith row. So you can take that ith row and you can multiply it with a matrix, and this is the past. This will be more than the rank of that matrix minus epsilon. Or there exists a matrix for any component. There is a matrix so that if you take that row, you project it into a subset of them. This is going to be like the rank, so it's like Bernoulli half on that projection here.
Isn't there a different way to see it? If you looked at the Fourier coefficients of the distribution mu,
Yes.
you did them one at a time, right? These are just correlations of.
Yes.
So each one would give you just a binary vector, right? So you just take an inner product.
Yeah, it's extreme also.
Take
It's
an inner product with any fixed non-zero vector, right, of your distribution.
Yeah.
Right, you get a 1-bit distribution. By polarization, right? So I'm just converting the distribution on m bits to a distribution on 1 bit, just the inner product with the
Yes.
fixed non-zero vector.
Yeah, that's what you do. Yeah, exactly.
Okay, so when you do this, then you get a 1-bit vector and it polarizes.
Yes.
So that means that every Fourier coefficient is converges either to a 0 or to a 1.
Yeah. Or I
That
think.
just means that that's a subspace. Right?
Yeah, but you need to show two things. So if I understand what you're saying, that you just take yi over all, so yi of j over all the j in S. You look at all these
That's the
things.
inner product with the
Yeah, so that's what I'm doing here.
Okay.
But you need to do two things to prove this works. First, you need to prove that you don't lose anything by looking at the subspaces. This is this type of argument. That this is actually containing.
Why do you need to do that? I mean, if all Fourier coefficients of
Yeah.
the
So yeah, you use
outcome
Fourier.
distribution are zeros or ones, it means that this distribution, the output distribution, is supported on a subspace.
Yes. Oh yeah.
These are the only
Yeah,
distributions.
that's enough to show it's supported on a subspace. But and this is where it was interesting to prove that this was like 2 minus square root of n.
Oh,
I
okay,
could not.
so
Yeah. Yeah, so indeed the proof is broken like that in the paper. I first proved this independently of that, and then I just use that for that part here. So again, it's efficiently invertible, and the relevance of it scales with them. The relevance of that setting is, for example, in compression, it's for Slepian-Wolf coding. If anybody here in this room has a string which is random, and you want to compress these things jointly, and you want to exploit the correlation between the strings, that's the Slepian-Wolf coding problem. So this approach, this result allowed to get optimal in terms of rate consumption source compression for Slepian-Wolf, which was.
So what's the connection between this problem you're describing and Slepian-Wolf?
Yeah. So this is a bit fast, but basically, imagine that everybody here has a string which is x1 up to xn. This is a first person, and then another person. Let's say 2 people. Everybody. This is, for example, the weather in Princeton. This is the weather in New Brunswick. And you know that they're correlated. So everybody applies the matrix Gn to their vector, but separately. That's why it's nice that this applies separately. Then, since assume you know what's the correlation of the weather in New Brunswick and Princeton, then we know which component will become with the pattern of this random and deterministic component here. We know it ahead of time. So transmit to the central station only the random components. Everybody does that, and then the central station has everything to reconstruct both sequences, and it requires a total of entropy of mu times n components, which is less than if you don't exploit the correlations. So it was not known how to compress efficiently in the Slepian-Wolf setting, just like LDPC could not achieve the BSC setting. This was even worse. So polar codes not only I think are nice because they compare to LDPC things, but independently of that, they apply to network setting like here. I think that's one of the nice things about the polar code. It's a really new approach. So yeah, so I think I don't think I have time to discuss. I don't know. I have time, so I tell you a bit about Z. What happens? So see, the general picture is always the same. You take an object which is random. It could be a bit, like in the first part, or it could be an m bit in the second part. You apply that transform, that recursively take that random object and split it out until it brings it down to the corner, to the extreme sort of configurations. So that is something that is quite general. This principle, it's a bit like Krein-Milman theorem, but in a constructive, like a operational Krein-Milman. But now for Z, there's something slightly different. So imagine that x1, xn. So this is the case of Z. X1, xn are ID Bernoulli P. Or let's take them to be still binary, but instead you apply Gn like before on the x vector, which is the column vector, but say that you do this on Z and no longer on GF2. So you still have exactly the same balance equation. The entropy in X is the same as the entropy in Y. This is one-to-one map. This is n times the entropy of the P. This is still the sum of the entropy of the Yi given the past. Except that now this entropy, since this is no longer binary because you don't do modulo 2, so this is large, this could be potentially between 0 and log n now. Okay. If you think of the proof of the binary case, you still have exactly, because you still have this balance equation, it's again, you can again define a martingale. It starts at h of p, and it splits into two terms, but now these terms can escape the region 0, 1. They can become arbitrarily large. So the good thing is it's still a bound in martingale because 0 is still a lower bound. So you still have convergence. Yes?
Right, I just want to make sure I'm understanding so we're thinking things up. So before we were looking at, say, you want to send something over the binary symmetric
Exactly.
with error probability P.
Yeah.
So now
Now I'm going to sense, but I'm allowing my measurements to be much richer. Instead of being binary measurements, they can be Z measurements, or they can be basically, instead of bits measurement, they can be n-bit measurements.
measurement, what, I mean, does that mean alphabet size?
Wait, what it means measurement is that this matrix, when you apply it, the value of this Y are not bits, but they are of cardinality log n.
It is the alphabet size.
This is alphabet size.
Alphabet size is allowed to have log n bits.
Yeah.
Okay.
Yes. Indeed, my goal, if I manage to go to R, is to connect this to compressed sensing. But because in compressed sensing, your measurements can be arbitrarily precise. It's a measurement. Whether in the compression setting, everything is in bits. But so now, this martingale must converge. And again, you're asking yourself, when does this happen? Eventually, when is it that if you take a random variable which is over the integers, when is this convolution, the sum of the two, close to us? Yeah, only in 0, but it's actually not easy to see. So if you have a direct argument, it's not easy to prove.
On the non-negative.
So you want to show that this implies that h of x has to be 0, where delta goes to 0. It's not easy. So Yao was. So what we need actually is a bit more. We need to prove the following, where z is a function that is actually only 0 at 0, and otherwise it's strictly positive. So the only way you can make this small is that this must be small. So these questions are being actually answered now independently of Power codes. I mean, people are looking at these problems because of additive combinatorics. This is like, when can this be close to that, or a question of this kind. But the only known result is that this is more than half when the entropy is large enough. This has been proved by Tao in 09. And indeed, you can show that there exists such a function.
What do you assume on X?
Is torsion-free group, but assuming that I'm restricting myself to the X which are on Z, on the integers.
And X itself has positive entropy.
This is a discrete entropy.
Yeah, but what do you say? I mean, if X is a constant function.
Oh, you mean strictly positive? Sorry.
Strictly positive.
Yeah, but well, this is little O of 1 when H becomes large. So you rule out the 0 entropy case. This is for entropy of X goes to infinity.
Okay, yeah.
We want the other case. We want when entropy is small. But we need actually to show that there is a continuous there's a function that does not depend on once for all there, and that this happens. So this holds, but as I'm saying, if you see a quicker argument to prove that there exists such a function, I'll be happy to hear. We proved it with Agiga, Choar, student at TPFL, and myself and Talatar just recently. 13. I feel like the proof is way too complicated. It's basically you have to break this into two regimes: the distribution which are delta-like, which have a large L infinity norm, and then the ones which are like could be like binomials, or could be self-similar, where that gap could be small. But it's not easy to find a clear argument. So, but what this implies now for the polarization is that this actually the only fixed point of that process is now zero entropy. So you no longer have an polarization, but you have an absorption phenomena, like we call it. So what you can show is that if you count how many components are more than epsilon, this now is little of n. Yeah, so this is very slow, I think. N log n, n by log n.
Log n or log n?
N by log n. N over log n.
Couldn't be any better than that, right?
It couldn't be any better than that because log n is the max you can get. You're right. But so what this means is that if you allow yourself to have measurement on alphabet n or log n, then you only need a vanishing fraction of measurements to contain all the x. Instead, if you go now to R, and if your distribution are completely continuous, and you apply that same matrix, then you're in trouble because first of all, you can normalize the matrix over R to be like this one instead of 1, 1, 0, 1. It's just a matter of normalization. But if you take Gaussian IID, then nothing will happen, clearly. However, what happens is if you take IID, but which are non-Gaussian, but
so
from...
Can you explain? I didn't understand. Why don't you get anything if you apply this rotation? It's a rotation.
It's unitary transform, this map. But what happens is that if you take them to be a non-Gaussian, IID from some distribution, let's say uniform, what seems to happen is again an absorption. So meaning here everything was becoming deterministic except little of n. Here,
become Gaussian?
Here I think it's the other way around that happens. Basically you get only a little of n of fraction that becoming delta-like, but very few. And the majority of them, so n minus of these, are becoming like IID Gaussian, I think.
So also there's this, I mean, like there's Barron's version of like the central limit theorem, where you can look at, the entropy, the Bregman projection.
It's very different.
Gaussian. This is different?
Yeah, very different because here we are targeting each of these components. If you apply this matrix, okay, to the power tensor product, to your ID, which is non-Gaussian, ID uniform, each component marginally becomes Gaussian by the central limit theorem. Yeah. And you could use Baron to prove that or something else.
The issue is that the multidimensional...
The issue is that the ith component given the path may be very different than Gaussian. So it's this structure that is tracked here. So this is the proof is not finished for that, but I think that's what I conjecture happens.
So the matrix here is the Hadamard transform?
Hadamard transform, exactly, yeah. So this would be an efficient way to basically do noise shaping. Or like you have a noise which is not Gaussian, you could efficiently make it ID Gaussian. But I think that I just want to finish with that. Perhaps the most interesting case in this line of work is if you take a distribution which is a mixture. So you are on R, and let's say that your distribution is a Gaussian with mass delta and a delta of 0, for example, of mass 1 minus delta. So it's not continuous, it's not discrete, it's a mixture distribution. And you apply that Hadamard transform to it, but you analyze it with those tools. You analyze basically recursively. Okay, so then there's something cute that happens, which is if instead of tracking the entropy, which is not defined here, there's no entropy defined for this distribution, you track the Rényi information dimension. this is simply the name of tracking how much mass there is on the non-discrete part of the distribution. So for a given distribution mu, assuming it's not singular, you can always decompose it into a discrete part and a continuous part. And the mass on the continuous part is this Rényi. In that case, it's just delta. So how much discreteness there is in X is still how much discreteness there is in Y, because this is a one-to-one map. This is still n times the delta, because each components are independent in X, like before. And this, you can show that this Rényi entropy breaks down again into this chain rule. This is what? This is given that you observe the past components. How much is yi discrete or continuous? Or how much is yi continuous? So we know that this must be between 0 and 1, because this is a single random variable. And again, this polarizes. You can show that this goes to 0, 1. So that means that if you have a distribution which is a mixture, and you have a vector which is highly different mixture, it's a large vector, but there's a strongly dominant mode component value. If you transform this with Hadamard, and if you look at the highest component given the past, you will look either very almost discrete or almost fully continuous. And how many components are becoming discrete? Continuous is n times delta. So this
Here, which components are going to come from the, I mean, if I give you a sample from this distribution, I can see whether it's 0 or not 0, whether it's coming from the discrete part or the continuous part. So can't I just take my data, split it up to a discrete part and a continuous part, and just transmit them separately?
Yeah, I think you have it right.
That's more or less what you're saying. That's going to happen here. Some of the components are going to become discrete, some are going to become continuous.
Oh, that this goes to 0, 1, I don't see it directly, except that you have again a martingale, and that martingale must converge, and the only. But what is true is that this is a much weaker measure of information, how much mass on the continuous part. And the good news in that setting, you can exactly track this process, as opposed to the other settings where we don't know who goes to 0, 1. Here, this process is given by the following. You take delta, and you either compute this, or you square it. Take that process, iterate it. This defines a pattern, which is chaotic, of some components that go to 1 and some components that go to 0. Take an Hadamard matrix. Only keep the rows that are components corresponding to high Rényi information dimension. And this gives you a matrix that allows you to contain all the Rényi information of your original vector. So the question there is, does this allow you to sense, to do dimensionality reduction? And we don't have the algorithm now, but numerically it's clear it does. So basically, if you have a large dimensional vector which is distributed according to that, there's a very smart pattern in the Hadamard matrix. So it's like you take your big square Hadamard matrix, and you delete rows, but according to this pattern from this process. This allows you to actually sense the vector at a rate which is n times delta. So compared to compressed sensing would be n times delta log n. So you don't have that log n term like in compressed sensing, but because we are in a probabilistic setup.
Does it have to be a Gaussian and a mix?
No, anything.
Anything continuous and anything discrete?
Yeah, anything continuous, anything discrete. So it could be that you have two spikes. It could be that you have multiple spikes and you have some arbitrary shape. This still polarizes to 0, 1. So it's not just sparsity that is the keyword here. Because this is not sparse if you have two spikes. It's not sparse in the sense of compressed sensing. It's just if you have a few modes that are dominant, that have a strong probability, and then you have something which is continuous. And then there will be a pattern to represent that large vector with much smaller ones. And how much reduction is governed by how much continuous mass you have at the beginning. So I don't know if I don't think it will, but I thought it could maybe help with this construction of RIP matrices, because this is a deterministic matrix now. It's fully deterministic and structured, and the pattern is non-trivial, which is like, oh, perhaps that's an effective way of. But it's different setting because we are in the probabilistic setting. The x is not any vector; it's a random vector. But what this says is that in that setting where x is random and under that measures, we can solve the RIP sort of problem with that formulation. And you get not only a deterministic matrix, but the very structured ones. So it's like the only thing is, as I said, that we don't have proof that the recovery algorithm works. We just plug L1 minimization and message passing algorithms, and this works very well. There's more work to be done here. This is 13, this result. And it's myself and my student, Agigat Shoar. So yes, I think it gives you an overview that this principle of recursively applying the matrices and is in these different settings. So GF2 to DM, and this Z and R. Thanks.